let's look at an example where we're, going to drop something like a stone off a cliff over here. And we're still on vuast type problems. And in the question, we have a person standing at the top of the cliff, and they drop a stone from the top of the cliff, and it's going to hit the water. And we're told that the cliff is 65 meters high. So we're going to take it that S then is 65 meters high. And so we're going to do this as a normal vuast type of problem. And when we usually approach these types of problems, it looks like we don't have all of the information in the question in order to answer it, because we're only given one height. And so it looks like we can't do vuast problems, but we can't solve it correctly. But we just follow the normal steps that we would for any vuast question. So we do V, U, A, S, T, like this. And we start filling in the values that we can get from the question, or that we can infer from the situation. Now that's the difference compared to the other problems that we've met, where it's a car accelerating or something like that. So if the person drops the stone off the cliff, well then obviously the starting velocity is going to be 0, because they're just holding their hand out and just releasing the stone. So the initial velocity here is going to be 0. Now that's not necessarily given to you in the question, but you'd have to know that simply from the situation, right? Now, we don't know what V is, because that's the final velocity that the stone would hit the water with. S we know because it was given to us in the question as being 65 meters. The time we don't know, and then the acceleration is something, again, it's not given in the question, but we still know it. We can infer it from this scenario, from the situation. Essentially, we're saying that the displacement of the stone would be this way. We've given that a positive value here, 65 meters. So in general, we're setting up a situation where that's a positive direction there. Plus VE is just shorthand for positive. So we're saying that the downward direction here is positive. Now, if the downward direction is positive, then we can say that the acceleration down this way is plus 9.81 or 9.8 meters per second squared. Now, how do I know that that's the case? How do I know that it's going to accelerate at that rate? That's the acceleration due to gravity. Once I release the stone, it's going to accelerate, it's going to pick up speed, and it's going to pick up speed due to gravity. Now, in a real situation, there'd be air resistance and everything here, and that's going to affect the speed. But we're going to assume here that there's no air resistance, and that the speed is just going to pick up in a normal way following this 9.8 meters per second squared acceleration. Okay, so the next step that we have then when we're doing this is to write out the equations. So V is equal to U plus AT. V squared is equal to U squared plus 2AS. And S is equal to UT plus a half AT squared. Okay, next we go along, the next step is we go along and we kind of put marks under everything that we have, that we've been given in the question. So we start with U. Anywhere there's a U, we'll put a little mark in under here. So we have U. A we can mark off as well. And S. So anywhere there's an S, we can put a mark under that. Okay, so what can we solve immediately from this? Well, if we look at this, the first equation, we've got V here is unknown and T is unknown. So we can't use this equation immediately. We can't start with that. The next one here, we've got V here is unknown, but all of the other variables are known. So we could solve for V straight away. We could get the final velocity of the stone just as it hits the water. And if we look at this equation here, we've got S is known, U is known, A is known, and the only variable that's left in this equation is a T variable, which means that we'd be able to work out how much time it took for the stone to drop this far. So let's start. We'll do part one of this problem, which was to work out the final velocity of the stone just before it hit the water. So there's we're going to use this equation here because we have V here and all the rest of this is known. So V squared, a V term I mean, is equal to U squared plus 2 AS, like that. So V squared is what we're trying to find with V here. U is going to be 0, so that's going to be 0 squared, plus 2 times 9.81, 9.8 or 9.81, times 65. Okay, V squared is equal to, well, 0 squared is 0. So 2 by 9.81, I have to get my calculator. 9.81 by 2 by 65, and that gives me a value of 1275.3. But this is squared, so I want V on its own. So in order to do that, I would have to do the square root of this, which means I have to do the square root of this side. I can show that like this if you want. So I'd have to do the square root of that in order to get V, which means I'd also have to do the square root of that whole thing there. So what I eventually get is V is equal to, and if I do the square root of the value that I had there, I end up with 35.7 meters per second, and that's the velocity. Now, in order to work out the time now, I could do this two ways. So I figured out what the velocity is here. It's 35.7 meters per second. That's the final velocity. So I could go back and I could redo this now using, because I've got V, I could essentially put a little line under here, anywhere that I've got a V term like this, and I could say, right, well, that one's solved out. This one now I could use, because I could work out t this way, and this one I could also use. Now, which is the better choice here between these two? Because I can use either one of these two in order to solve it for part 2 to get the time. I would say that this one is a better one, even though it's a more complicated looking equation. The reason is that if I got something wrong here in my calculation, so that I worked out V incorrectly, that will have no impact on working out t here. I could get this value wrong. I could miscalculate here, and then use this equation and still get the correct t value, still get the correct time value. So I'm going to use that this equation here, the third equation. So I'll write down the equation. S is equal to ut plus a half at squared. So S is 65. Is equal to ut, that's 0 by t, plus a half, a is 9.81, times t squared, if we're trying to find t. Okay, well, 0 by t, that's going to go away, straight away. So we're now just trying to solve for t here. So we bring down the 65 here on this line is equal to, and now if I do a half by 9.81, I get 4.9, we'll just do that, 4.9. 4.9 times t squared. Now I've got this t squared term. I want to get this t squared term on its own, but it's multiplied by 4.9. So I have to divide this side by 4.9, which means that I have to divide that side by 4.9. So first I'm going to flip these over. So this is 4.9 t squared is equal to 65, just because people find it easier to have the unknown variable on the left-hand side of the equation. So t squared then is equal to 65 divided by 4.9. So 65 divided by 4.9 would give me a value of 13.265. And so t then, I'd have to get the square root of this to get t, which means I'd have to get the square root of that in order to, it's an equation, so you have to do the same on both sides. So we get the square root of that would give me a value of 3.64 seconds. And that's how we would solve a problem like this, where it looks like we don't have all of the information that we need in order to solve the problem. This is usually the case with either throwing something up into the air or dropping something, because you have to assume that the acceleration is due to gravity is 9.8 or 9.81 meters per second squared. And also often, when you release something, to just drop it, the initial velocity is 0. Or if you're throwing something up into the air, you release it at a particular velocity, but once it gets to its highest point, its final velocity is 0, and that's usually not said in the question. So just to be aware that you have to kind of use both the information given written in the question and information that you know about the situation, about the scenario that the question is based on, in order to answer the question correctly.